My name is Miha. I come from Sinergise, and I'll be speaking about our experiences developing and using our on-the-fly analysis-ready data that Sentinel Hub is producing. Sinergise is a company based in Slovenia, a small business with 50 employees, and our history is in developing large registers and administration systems for public authorities. We worked and still do work in property administration and mass valuation of real estate, and as well also in agricultural land administration for agricultural ministries, mostly in Europe. They deal with government payments to the farmers. And in that line of business, we've often came across satellite data. And we were often frustrated by the amount of work that needed to be put into that in order to just display the data in a web browser. So that was our first interaction with satellite imagery. And when the Sentinel-2 was announced, we realized that its high revisit time and its high spatial resolution would make it a perfect fit for monitoring agricultural land and helping our clients. But from our past experience, we knew that the traditional ways of working with satellite data just wouldn't scale to that revisit time and to that amount of data. So you wouldn't do the handcrafted processing and manipulation that you used to. So you'd need some automated processes and a better way of dealing with this data. So we envisaged Sentinel Hub as a service that would, on one side, access different kinds of satellite imagery or other raster data and expose that simply in an OGC interface or a REST API to be directly consumable by web GIS applications or mobile apps or desktop GIS or accessible via scripting. Now, that was a good plan, but once we did some calculations, we realized that we just didn't have the budget to store 100 terabytes of new data every month. We had a couple of servers, but not nearly enough. So initially we said, okay, then maybe we just do Slovenia or the Balkans and make an image pyramid and make that run smoothly. But then in preparing for this, two things happened. We realized that the data would be stored in JPEG 2000, which is an image pyramid itself. So maybe we didn't need to pre-process it. We just need a way to access that with a range query to get just the bytes that we need and render a small portion of an image. And the other thing was Amazon said they would provide a mirror on their S3 cloud of this data, which means that we didn't have to invest into storage. We could just use their storage and access data directly. So we decided to go this way, access JPEG 2000 directly and use the Amazon storage. In the process, we came to a deal with Amazon where we take over the ingestion of the data onto the Amazon bucket and curate the data set of Sentinel-2 on Amazon. And in exchange, we get insight into how data is organized, and we get like first-rate access to that. So the decision was to process on demand and on the fly as much as possible. So because we don't have a budget, we're just 50 people, a small company, and everything was self-funded. We said, okay, we don't do storage and pre-processing, we process on the fly. And about 6 months later, and Of that, there was about 3 months of optimizations and 2 rewrites of the whole library. We came at the Sentinel Hub playground, which lets you access any scene from Sentinel-2 seamlessly at any resolution. And it lets you choose from different products that are all computed on the fly and all rendered directly from the Amazon bucket. You can select a date from the full archive, and the images are rendered almost instantly. You can check it out yourself. It's a nice thing to play with. And it really gives you full access in full resolution to any Sentinel-2 scene. Since the early days, we've expanded this to include Landsat 8 data and MODIS. And we have other applications that do similar things. This application and the service is quite extraordinary because it really runs fast. And to understand why we think that about 1 second, which is the, let's say, the average response time from the service, in that 1 second, what our service does is it makes a query into the catalog to find which scenes are applicable to the request. It downloads the portion of the files that it needs. It does the decompression of JPEG 2000. It does reprojection into the user selected coordinate system, which is normally WebMercator, or it could be anything else. It does some pre-mosaic filtering. This would be some basic statistical atmospheric correction that we do, or radiometric conversion for Landsat data. It does the mosaicing of different scenes. It executes a custom scripts on every pixel, so it's a custom JavaScript that I'll talk about a bit later. It does some post-mosaic filtering, like contrast enhancement, and it encodes the output image as JPEG, PNG, or GeoTIFF. And this is the distribution of response times, so you can see that majority of responses complete within 1 second. The auto-rectification that we do sometimes in the pre-processing steps is also part of the on-the-fly processing. This is done primarily for Sentinel-1, but also Sentinel-3, in which data is not auto-rectified in advance. So this is the difference that I can show between auto-rectified and non-auto-rectified Sentinel-1 data. And the custom script that we execute is really just a simple JavaScript. I get a pointer. So the user just specifies a return statement of a function. The inputs are values for bands 4, 3, and 2. That's red, green, blue. And you can execute any JavaScript expression that you want on this. The input into the script are physical quantities, so this is relevant for analysis-ready data. These are reflection numbers, not digital numbers from the source file. The input is already warped into the requested coordinate system, so you don't have to deal with that as a user. It's already rescaled to the requested scale, so sometimes the script would get 10 meter pixels, sometimes it would get 160 meter pixels. And it's already auto-rectified in case the data source itself is not. Now, this is the simplest script that you can do. That's a true color rendering, but you can also do much more complicated things, like this natural color with shortwave infrared highlights to show the lava flow in the volcano. Or you can do a decision tree classification, like this one that we took from a scientific article. Just wrote a simple script to encode all of these decisions, and immediately you get the image in an application. So this is really useful because having this capability allows the user to play around with the data, to experiment with expressions, and to evaluate them on any scene anywhere in the world right away. Then the next thing that's kind of analysis ready related is the time-lapse, which we implemented in the EO browser application. The time-lapse allows you to select a time frame, and it loads all of the images from a sensor in that time range. We implemented a simple cloud pre-screening for this time-lapse functionality, which only uses 3 bands and a simple decision tree, and is evaluated at a much coarser resolution. And then when the cloud pre-screening is completed, we just load those frames that don't have too many clouds, and we do that progressively. So that's another thing that's maybe important for analysis-ready data, is to allow asynchronous progressive loading of frames as the user requests them, or to allow filtering based on some simple calculation with a coarser resolution. So this is an example of the recent fire in California, shown here in a SWIR composite. Another thing to note is that all of these functionalities, like time-lapse and the other things that I will show, are available on any composite that the user defines through the custom script. So it's really useful for getting a feel for some data for some time range, and to explore what an analysis-ready data stack would look like. This is an example of the Krakatoa volcano, again with shortwave infrared highlights to show lava flows. And this is an example of NDVI time-lapse of an agricultural field. And we can also do that on send to core level 2A classification data. These are the classes that come out of that product. With classification data, something that's important for analysis-ready discussion is that categorical data types don't really afford rescaling naturally. So if you want to combine 16 pixels at a lower resolution, you have to think about what does it mean if you have 5 pixels that are vegetation and 11 pixels that are bare land. What is the low resolution pixel going to be classified as? And that's something that is not very well studied in the literature, or something that's not even discussed in the L2A products, but it might be important for analysis-ready data if we want to support access at any scale. So another interesting feature that we have is this statistical API that takes as an input a layer and a polygon or a single point, and computes the time series statistics over that polygon. So you get a histogram of different values for every step in the time series. Here again, we've used cloud pre-filtering with this simple 3-band decision tree. And again, we have a progressive loading of data, so it takes a couple of seconds, but you can get 2 years or 5 years time series in real time, computed from raw level 1C or level 2A input. The important thing here that is relevant to the analysis-ready data is that for such a chart, the region of interest is really small. So It's either 1 pixel or a very small field, a polygon. So it doesn't make sense to download whole tiles to compute just that. You need to be able to specify a small area of maybe 100 pixels and get data for only that small area. Then the next big step that we did is allow multi-temporal processing and analysis. The examples here show progressively lengthening time ranges of multi-temporal mosaic over Ireland. So multi-temporal processing is essential to be able to get cloud-free mosaics, especially in Ireland, which is really cloudy. And the functionality, when we added it, was quickly picked up by our users. One of our most active users is Pierre, who quickly made a mosaic of Europe and Turkey. This is an example of a max NDVI mosaic, so just getting the green stuff, and it helps screen out the clouds. And with multi-temporal analysis, you can do interesting things like show fields in various colors based on whether they're vegetated now versus 3 months ago versus 6 months ago. So you can see which fields have just been sown and which have just been harvested. This is a nice comment by one of our users saying that the JavaScript functionality is so easy that even his mom could use it. And it's true. So the JavaScript is really similar to what I was showing. But the only difference is that you get the full stack of pixels for the whole time range that you can then apply expressions to. Then some other examples, just showing nice pictures because that's what we can do in the satellite business. That's from Pierre Marcus again. A mosaic of 2 months on the left and a mosaic of 7 months. And then a mosaic of Europe with 9 months of data. And another one of Mediterranean with some water highlights. And then a 12-month mosaic of near-infrared and short-wave infrared data for the United States. These have all been created with the EO browser application, and Pierre did not use any other processing except for the JavaScript that he input into the web application. So with this functionality, we developed a production mosaic for New Zealand for the whole year of 2017. There were about 8,000 Sentinel-2 tiles used in the production of this mosaic. We used an algorithm that took the first quartile of all cloud-free pixels. We used Sent2 core masks for cloud screening, which were quite okay, but still had some false negatives. So that's why the quartile comes useful. We did it with 3 bands for output and the scene classification layer for filtering. And we did all of the processing with this multi-temporal scripting on the server side in chunks of about 300 by 200 pixels. So that was the analysis-ready tile size. And the result is quite satisfying. It's balanced. It shows detail. And the clients were very happy with it. You can see it on the internet at the New Zealand government site. Then we did, for the European Union, a quick project doing a Sentinel-3 mosaic for 2018 with a bit shorter time range, but because of Sentinel-3's higher revisit rate, we still could get enough cloud-free data. In this case, we used desktop processing, so the processing was not completely done on the server. Only the separate scenes were fetched from the server. So we did it in chunks of 8,000 pixels, and we included the near-infrared. This was done without any atmospheric correction, so the result is a bit hazy. And we did the near-infrared as well. Then we also used the same functionality in the Sentinel-2 global mosaic, which Michael was speaking about earlier, so be sure to check his presentation again if you're interested in this. This one was a bit more complicated because we used all of the Sentinel-2 bands, and for filtering we used scene classification, cloud probability masks, snow cover masks, and the view zenith data from the Sentinel-2 metadata. So this is another thing that's important for analysis-ready data, is to include all of these auxiliary rasters into the stack as it's produced. And this will be released soon, so it should be a nice data set to be used for science or for communication with the public. Just a couple of words on the current status of the Sentinel Hub. We have a lot of data sources from Sentinels and NASA sensors. We handle about 50 million requests per month. We've ingested in this time about 50 petabytes of data into the service and transferred out about 1/10 of that, which is in line with the previous presentation saying that the user does not need that much data, but the processing does. I'm going to skip on this. And since I started with the cost, I'll just say that we're keeping the costs low. So this is the monthly service charge for the servers is about $6,000, which is not that much, and we can handle that. We do some machine learning with these capabilities. We developed our own cloud detector because we weren't happy with any of the existing ones. And it's pretty good, and it's open source. And we're doing a EOLearn Python package, which handles analysis-ready data in EO patches. EO patch is an object that combines all of the data that are input into the machine learning algorithm in one Python object, and that includes data that have temporal component, as well as data that don't have temporal components, and it includes masks, measured quantities, and vector data. So this is another thing that may be useful for analysis-ready data. With this EOLearn, we have a lot of useful tasks for Earth observation processing, like the co-registration, which helps to minimize the jitter that we see on the left side, which does not have co-registration. On the right side, we use this task to shift the images slightly. And to sum up, our recommendations for ARD is to try and set up the system so it doesn't need a lot of pre-processing, to enable production of ARD at any resolution, to allow retrieving a subset of data, even a single pixel temporal stack if necessary, and to include useful metadata. And the final thing, the cloud mask is still very important and still a very much unsolved problem, at least not completely. If you need more info, there's some links. There's the applications and GitHub repositories, which you can try out, and I leave you with a collage of some of the images that our users produced using our platform. Thank you.
Since we're running a bit behind schedule, maybe only one question, if there are any. Okay. Oh, yes.
You said it's a little, if you go back to the slide with what you want out of ARD, oh, back forward again. There we go. Pre-process as little as needed. I'm not sure the polarity. You're saying process enough that you have to do as little pre-processing, or do as little pre-processing to the data before giving it to you?
Well, both. Find standards and recommendations and practices that allow us to do as little pre-processing as necessary. And for us as an intermediary that takes data in and serves it to the client, it's cheaper to take less data in. So if you can pre-process in a way that you're not making 3 times the amount of source data, but just maybe 1.2 times the amount of source data, that's good for us. Because we can do some pre-processing or processing on the fly and save on storage. So we'd much rather have you design and develop an algorithm that runs fast and publish that algorithm so we can run it on our platform on the fly than having you pre-process the data and send us a petabyte of something.
Thank you again.